Okay, Newton's project. Law 1. An object at rest tends to stay at rest unless acted upon by an unbalanced external force, and an object in motion tends to stay in a constant linear motion unless acted on by an external force. So, in this example, we have a truck and a ball. The truck is the external force, and the ball is the stationary object, right? So, I slowed it down so that way I could talk more. So as the truck is going to hit the ball, which is stationary, the force applied on the ball will be unbalanced in the what we'll call the left positive direction. So the ball will slide to the left until friction acts on the bottom of the ball, causing it to spin. That will come up later on in the video. But as you can see, as it slid, it was in a constant linear motion, but then once friction came on, it was an external force, which ended up slowing the ball down. Now, as this path continues, we will see a second example of an object in a constant linear motion being stopped by an external force or changing direction. This would also work when you turn the truck, but we're not doing that. We're just going to use this giant wall as our stopper. So as the truck hits the wall at 42 miles per hour, it immediately stops, because the force of the truck is less than the force of the wall, meaning that the force of the wall just stops the truck dead. So here's the same example again. Now I have added in some nodes which show the velocities of the different nodes on the truck and on the ball. As you can see here, as the truck hits the ball, the nodes point straight left, meaning that it is going to move in a constant linear path to the left. And then, as you can see, I think almost now, it's kind of hard to see my little video window here, but as you can see now, they are starting to rotate because of friction. So friction is causing the ball to rotate and thus slow down. So there we go. Now the lines are becoming more and more and more clear. Pretty soon I'm going to bring it up to like full speed or something, so that way we can show you what happens when the truck hits the wall with all of the different velocities. As you can clearly see, the velocity of the ball is increasing with friction and the force originally applied on the ball. Of course, when it gets hit by the truck again, then it will accelerate again. And as the truck hits the wall at around 36 miles per hour, the velocities shoot forward, then they shoot backwards, and then it's stopped. Because, again, the force on the wall is greater than the force applied on the ball. Okay, law number 2. The acceleration of an object is directly proportional to the net force and inversely proportional to the mass. So here we have two of the identical trucks. The only difference is the red truck has a cement mixer on the back and the black truck does not. Now, as we can clearly see, the truck with less mass, meaning the black truck, is much faster than the red truck because it has a greater acceleration. So clearly it won. Here's another example where we used a sports car which has a higher net force than the truck does, therefore having a much greater acceleration and has a lighter mass. Wins the drag race unbelievably ahead of the truck. There's the truck. So, law number 3, for every action force, there is an equal and opposite reaction force. We demonstrated this in several ways. Here are the velocity nodes again. So as you can see here, when the tire comes in contact with the ground, it is exerting friction backwards, but the car is accelerating forwards. So for the amount of friction going back, there is an equal friction, or equal acceleration going forwards. Here I have added in a little rope to the wheel, so that way you can see where it comes in contact with the ground, that it is moving forward when the wheel is moving in the opposite direction. Here's just a third example of it. Okay, back to the soccer ball. This is essentially a giant tire, in this case, where on the ground it is exerting a frictional force backwards of the motion. So as it applies friction going backwards, as you can see here, this is an upside down view. As it exerts friction backwards, it is moving forward, making an equal and opposite reaction force. Okay, these are just bloopers, so I hope that you enjoyed this part. Okay, doodles.